So I'm very happy to be here so that we can, have a short overview. Actually, it's not an overview, but a short looking back into the past 30 years of what has happened in the field of scientific binary decompilation. Honestly, when Arvind asked me, hey, do you want to give a keynote? I was like, I've been working on binary decompilation for a while, right? So I was just wondering, how many years have we been working on this topic? And I took a look. I realized the very first paper was published in 1993. I think, if I'm not wrong, the very first paper that targets the problem of binary decompilation was published in 1993. And I was amazed. I was like, wow, if we count it properly, counting this year as well, this is actually the 30th year. So, it's a very big honor for me, of course, to give a keynote at BAR, but also to give a keynote on this specific topic at this 30th year mark. And honestly, the other thing that I want to say is, if let's say we rewind the time all the way back to 1993, and you were going to ask me, hey Fish, how much time do you think we will need to solve this binary decompilation problem? I'm not going to give you like the number of 30 for sure. I would probably have said 10, 15, but who am I to say that, right? I'm still a kind of a newbie in the field of binary analysis, and how much do I know, right? But that also says, hey, binary decompilation is a very hard problem, and even right now, I don't think we are anywhere close to the final solving of this problem. So as Arvind has already predicted, I do believe that crown of binary analysis is decompilation. This is not only because decompilation is a problem that we haven't solved, but it's also because decompilation uses a lot of techniques that binary analysis field depends on, right? Let's say we are doing vulnerability analysis on binaries. A lot of the techniques that vulnerability analysis relies on are also techniques that are fundamentally mandatory, fundamentally essential for binary decompilation. And this is why, if all of these techniques, or if all of these techniques in the field of binary analysis are perfect, all of those problems are solved, we should be able to have binary decompilation as a natural outcome. But of course, we have so many problems in binary analysis as well in decompilation. This is why we still have the BAR workshop. So now the question is, why do you want to do binary decompilation? Obviously, there are many applications, right? Suppose right now you have an executable, you have a binary file, right? And you know that my CPU can run the code. My computer, my laptop can run this file, but as a human being, I have no idea what this file does, essentially, right? So that is the problem of program understanding, right? How can I understand the piece of program? How can I understand a piece of binary file, right? Just seriously, how can I do that? Well, if you have source code, right, you can open the source code. You can start reading from the first line to the last line of that file, and then try to understand everything that you have read. So if you understand that target language, hopefully you will be able to understand the program, right? But of course, understanding programs is hard. Understanding binaries is only harder. A lot of other applications include code reuse, right? One example, I'm a big PC game player, and then one game that I played a lot in the past when I was young is called Pharaoh. It is a city simulation game, and now they are building a new version of it because the very first version was released back in 1999, and now after 20 years they're building a new version. They didn't start from the original source code because they couldn't find the original source code, as far as I know. Right, they posted this in their official Discord channel, and then I was like, wow, and we all know this. Even vendors, official IP holders, companies, large companies, supposedly they should have very good software engineering practices. They still loot source code, right? Let alone those companies that are using a lot of third-party libraries, using a lot of third-party code that the source code was never disclosed to the vendors in the first place. We also want to do vulnerability discovery, right? Doing vulnerability discovery on binary code is hard, We get several top-tier security conferences papers published on this topic every single year. The problem is not solved yet. And we have a lot of tools in source code that are able to discover vulnerabilities in source code. Can we directly use those tools on binaries? The answer is no, right? Because we don't have a very reliable way that converts binary code to source code, right? If we have reliable decompilation, we'll be able to perform source code analysis, especially when analyzing binaries generated from those non-traditional languages or compilers. All of a sudden, you will be able to decompile binaries into C code and then analyze the C code using existing tools. So one concept that I really like, I'm not even sure if this is a term that I came up with at some point, but it's still a concept that I really like. It's called software democracy, right? So everyone's talking about supply chain attacks. Everyone's talking about supply chain security. The fundamental problem there is everyone using software is essentially blindly trusting the vendors and the supply chain. And right now, when we're using software, we literally do not have any way to tell whether software is performing or is going to perform as expected, right? Decompilation is, I believe decompilation is a fundamental stepping stone for us to start solving this software democracy problem. How can we give end users control of what software they are running, of what behaviors the software that they are running are allowed? So before we start talking about the current landscape of binary decompilation, let's first talk about what are we talking about? What do we want to decompile when we're talking about binary decompilation? So we're actually referring to well-formed executables, library files, object files, or even machine code snippets. So one thing I realized while I was working on the slides is that binaries is actually not a well-defined term. When I'm talking about a binary file, what does it mean? Is it an executable that has maybe hundreds of thousands of functions? Or is it a library file? Or is it an object file, maybe it only has several functions from a single C file? Defining this is important because I've seen papers, and I've seen papers accepted, published, claiming that they work on millions of binary files. In the end, they are actually object files. Okay, so when you're reading the paper, you might be expecting, wow, millions of programs. That's actually not the case. So most of these well-formed executables or library files that we want to decompile, usually they're from C code. But not always. They can be, compiled from C++, from Crystal, from Rust, from Go, or from some other languages. But essentially, they're compiled into executables. Some extra requirements. When we're talking about decompilation, it's not only about decompiling ELF files for Linux, right? We may decompile Windows executables. We may decompile macOS libraries, and many other platforms. Now that IoT devices are very common, right? Usually we cannot really assume that the binaries that we are working on, they do not call external libraries. They do. Very often they do, right? How often do you see statically linked binaries? Not that often. In many cases, the binaries that we care about, they will use external libraries. And also, we cannot always assume that compiler optimizations are always disabled. Right? One big problem for why decompilation is hard is that, A, you work on stripped binaries. Binaries do not come with their debug symbols. And second, compiler optimizations are getting into the way that are making binary code much, much harder to be analyzed, much, much harder to understand. There are some no's. There are some things that we don't like, and I believe, at least for today's talk, they're out of the scope. We do not want to decompile obfuscated binaries. We do not want to decompile packed binaries. Go unpack your binaries first before you want to decompile them. And we do not like jitting. We do not like dynamic code generation. Right? For any code that's dynamically generated, let's take them out of this equation. Okay. So I want to set up the ground to say that binary decompilation is not an easy problem, right? If you don't really know how compiling or decompilation works, I'll just spend 10 seconds to explain it. Compilation is compiling is a lossy process. When you're compiling, especially after stripping, a lot of information is lost, right? Such as control flow structures, variable names, types, function boundaries, etc. They're all lost. A lot of these problems are, what binary analysis, or vulnerability analysis on binaries they really care about. Some of these problems are not what other fields or subfields in binary analysis care about that are very specific to binary decompilation. For example, control flow structure restructuring. So compiling is sometimes seen as a protection and an anti-reverse engineering technique. This is solely because of the information loss that happens during compiling, right? And then many people assume that if I compile my source code into binary code, no one will be able to understand it anymore. Well, that is without reverse engineering, without decompilers, that might be true, right? But now, if we are when we are working on this kind of advanced decompilation techniques, we really want to prove that this concept is actually very dangerous. And also, another reason why binary decompilation is difficult. Testing? Testing? Okay, very good. So another reason why binary decompilation is difficult is that optimizations really don't care about decompilation, right? When you have a compiler, the sole goal for the optimizations to work is they either care about the size, they want to make the binaries smaller, or they care about the speed, right? They want to make the binaries run faster. They don't care about if your code is decompilable or not afterwards, okay? So over the past 30 years, what have we achieved? So the very, very first scientific attempt, and honestly, I really want to, I need to read this name very carefully, maybe for 3 times, but that's a waste of time, so let's just do Dr. Cristina Cifuentes. She's the first, I think during her PhD, she was the first person publishing papers in this area doing scientific binary decompilation. Maybe there have been some, enthusiast attempts in the past, but they weren't documented nowadays. So, if you're thinking of whether you want to do a PhD or not, the answer is yes, right? This is the only way to make sure that your scientific contributions are remembered even after 30 years. So Dr. Cristina Cifuentes published 2 papers and then her final PhD thesis on the topic of binary decompilation. And a lot of the techniques that we're using nowadays were actually created back then, and then those techniques, those concepts and techniques, they're still here. So from that paper, right, a typical decompilation pipeline looks like this. You have a CFD generator that generates a control flow graph from the binary, and then you perform a control flow analysis to try to recover as much high-level control flow structure, such as if then else, while loop, do loop, or other types of loops based on what languages you're targeting. You recover that kind of structures as much as possible, and then you perform data flow analysis to recover variables, types, function calls, etc. Right? And after that, there's an optional restructuring step, and finally you generate C code. That's assuming that the output will be C. So, assuming that you've never written the decompiler by yourself, right? Let's just do this by ourselves. X86 assembly, that's something that everyone understands, I'm sure. Let's see how we can decompile this small piece of code. I'll give you 10 seconds for reading the assembly code. If the text is too small for you, you can use Zoom to log in and then take a look at the live stream. Okay. It's okay if you haven't decompiled it yet. I mean, there will be the correct answer will be shown there in a few seconds. It's fine. So following that pipeline, right? Let's do a control flow analysis. We essentially have 3 blocks. Remember, notice that there is a jump not equal, so there's a jump, right? We can use those jumps to break this piece of code into 3 blocks. One ends at 113B. The other one goes from 113F and then ends at 1148 because there's a jump going to 1148. Okay, so that's what the control flow graph looks like. We have the first block, 112D. And then it will do a conditional jump based on a comparison it can go to either 1141 or 1148. Okay, and at the end of 1141, it falls through to block 1148 at the end, right? This is very typical. This is a typical if-else, right? So essentially, what it does is that whatever I don't really know what the condition is at the end of the block 112D, but then supposedly it does some sort of comparison, and then it jumps, and then it determines if it's going to jump to the next block or not, based on the result of the comparison. And then we perform data flow analysis. We realize, oh, there are actually 4 variables that are used. One is at RBP minus 0x14. The other one is at RBP minus 0x4. Okay, so there are 2 variables. And then understanding how Linux ABI, Linux System V ABI works on x86, we know that EDI actually stores the first argument this binary takes, or this function takes, and then we just call the first variable RBP minus 0x14, which is named arg0. The other stack variable, we just name it var0. Okay. And we continue execution. Sorry, we continue our analysis, and that should be the C code that's generated in the end. It's actually not that hard, right? It's actually not that hard. So this binary decompilation problem, if it's not that hard, why am I still here giving this talk? It's because there are 3 main pillars. One is control flow graph recovery. The second one is type inference. The third one is control flow structuring. That they're not hard to when you have a simple program. When you have large programs, it is actually very hard. So let's take a look at each pillars, and after that I'll talk about some some relevant techniques. First of all, CFE recovery. CFE recovery is a very well studied. CFE recovery on binaries is a very well studied technique nowadays in the field of binary analysis. I wouldn't say this problem is solved, but we are achieving pretty good results on at least x86 and x86 64 binaries, and then we are achieving not bad results on ARM binaries as well. So there's an awesome paper published at I think it's Oakland last year, called it's a systemization of knowledge paper. It's okay. All you ever wanted to know about x86, x64 binary disassembly, but were afraid of ask. Honestly, I'm not a very big fan of the title, but this paper is awesome. So one thing that this paper did very well is the authors analyzed almost all binary analysis or all commonly used binary analysis platforms, and then they collected their analysis assumptions, they collected their analysis approaches, and then summarized them in one large table. And also, this large table is not everything. There's also a lot of data. There's a lot of information in the text, right? So if you have never read this paper, go read it. It's a very fun read. I'm not going into details about CFE recovery, right? But one thing that we realized from this table is that, different binary analysis tools are doing things differently. They have different assumptions. They have different heuristics. They have different, principled approaches for solving a set of, important problems during CFE recovery. Okay, so CFE recovery is very important for decompilation, because to generate perfect decompilation, a decompiler must know at least everything that the compiler knows. Why? Because the compiler uses everything it knows to optimize the binary, to optimize the assembly code. And if the decompiler doesn't know that much information, the decompiler will make incorrect decisions at times. Here's an example. So, non-returning functions. If you have never written a CFE recovery algorithm, you will probably not thought about this, right? You're like, hey, if we want to recover the control flow graph of some programs, let's just see, which instruction calls where, right? And then and every single call returns. That's actually not the case, right? And I think one key feature that every modern binary analysis tools is doing is determining whether a function returns or not. This is because Compiler does that. A compiler, when it's compiling the program, it knows whether a function returns or not, and if a function doesn't return, it's actually incorrect for the CFE recovery algorithm to add an edge from the call site to the block after it. Does that make sense? So if the actual characteristics for a function is not returning, and then in CFE recovery during decompilation, we believe that the function returns, we will be introducing an extra edge. Otherwise, vice versa, if the actual function returns, but for some reason our CFE recovery algorithm is incorrect during decompilation, we determine that, hey, that function doesn't return, we're going to miss an edge in the CFG. And that is a very big problem afterwards during the high-level control flow restructuring, because you will no longer have the correct graph to start with for this function. So now you're going to ask me, what does a compiler know? A compiler takes the source code. A compiler can determine if the function returns or not if it sees this function calls exit, right? If it calls exit, it doesn't return. Otherwise, it returns. Is it really that simple? No. Why? Any answer?
Well, the binary could crash, and the compiler could infer that the binary will never go to the return because there's like a no dereference point, and like no dereference pointer.
So that's not the answer that I want, because a compiler would always make the most conservative assumption. A correct compiler would always make the most conservative assumption, right? It's because if there's a pointer that's a null, a compiler would actually allow you to call to access the pointer, and it will assume that the access will actually not fail. There could be an infinite loop, and the compiler will actually figure out that there's an infinite loop and the function doesn't return. Some compilers will do. So, well, thank you for your support. I'll show you a crazy case. So this is a case that I found several months ago when I was fixing a decompilation issue in Anger. This is a function. The function that we care about is error function provided by glibc. So if you read the description, you will realize that if status has a status is the first argument you pass to this function, what you call it. If the status has a non-zero value, the error will call exit to terminate the program using the given value as the exit status. So that means this function can sometimes return, sometimes doesn't. What is the safe assumption for the compiler to do? Compiler should treat it as a returning function, right? Otherwise, something can go wrong. What modern compilers will do, if you take a look at GCC, you will realize that it will see if the first argument is a constant or not. If it's a constant and it is a non-zero constant, it will treat it as a non-returning call. Otherwise, it will be treated as a returning call. That means if you try any decompiler nowadays that's not Anger, you will see that it will always treat error as a returning call. And then what happens is that the decompilation result will be introduced with extra edges, and then the results will look messier than source code because of this. Okay, go ahead. Does GCC turn a call into a jump? There are compilation options that control that. So, but that is outside of our discussion today. Yeah. So there is another technique, right, for decompilers to figure out whether the call or whether the jump at the end of the function is a tail call optimization. If it is, it should be a call, right? Yeah, but that is usually up to compilers' discretion. Yeah. It doesn't need to be. It doesn't need to be. It can either be a call or a jump at that point. Okay. Good question. Type inference. The second pillar for decompilation is type inference, right? And in fact, when we're talking about type inference, the very first thing that we need to do before talking about type inference is inferring where variables are, right? And that's something that many people don't even talk about. Do we really know where variables are? Do we really know what variables are on the stack? And then like individual variables, they are individual variables instead of a cluster of variables that you're just accessing everything as a large array. In many cases, no, right? So that's actually a problem that I'll mention in a bit. When we're inferring types, what are we really inferring? We are inferring local variable types. We're inferring global variable types. We're inferring function types or function call types. remember that there's a difference between function types and function call types, or function prototypes and function call prototypes. Because you may know what the prototype of a function is, but then when it's called, it doesn't necessarily need to be passed in with the same type of, with the same collection of arguments or argument types that the function is expecting. Okay, and then in many modern decompilers, you actually cannot specify for every single function call what their prototypes are or what the types are. Right, you can only specify for each function that's called what the types are. Right, sometimes it gets a little annoying when you actually see, there are some you want to control every single call site in a fine-grained way when you're decompiling. So based on types, right, type inference, in the end you get types inferred. So what are those types? Types can be pointers versus non-pointers, signed versus non-signed versus unsigned, right? Signed int versus unsigned int. There are actually two different types. Standalone variables versus structs, okay, or struct members, and sometimes you also want to see nested structs, okay, or unions in many cases. So these are very natural. I just want to point out one thing, that pointer versus non-pointer is actually not that hard to tell, right? If you see, hey, there's a variable that gets dereferenced, it has to be a pointer, right? If you see there's a variable and it's never dereferenced at any point, maybe it's not a pointer, maybe, okay? Nowadays, there are papers claiming that, hey, we do type inference, and then the type inference we do can directly assist decompilation. While the only thing that they can do is telling pointers away from non-pointers, and then also reasoning about primitive types. Remember that without recovering a type that the pointers are pointing to, right, it's very close to useless for decompilation, right? It's possible that the techniques are good, but then in the end, you actually need to know more than just whether this variable is a pointer or not for you to have reasonable decompilation out of it. Also, there's also the question of how to infer the types, right, that are used by the decompiler. So, of course, traditionally we have a lot of dynamic analysis approaches to infer types. I used to have like a long list of papers that are doing dynamic type inference, and then realized, oh, they're actually not used by decompilers. So I eliminated all of them and only left the very first one, Howard. I believe the author is Asia Solwinski. I believe I read her name mostly correct. That was a pretty cool paper published at NDSS 2011. By the way, many of the papers that I will mention during this talk are published at NDSS. So I think, for some reason, I think NDSS is a very good home for decompilation of binary analysis papers. Thank you, NDSS. And then, many decompilers, or if not all decompilers, are actually relying on static analysis for performing type inference. Why? Because in many cases, you cannot run the target that you want to decompile, right? So to perform static analysis. So one of the earliest work, I don't think that's the earliest, but that's probably one of the most influencing work, is TIE, published at NDSS 11. And after that, we had a retype D from Grammatech, that's PLDI 16. So their ideas are always, collecting type constraints by, kind of performing static analysis, performing a data flow analysis, tracing how the program executes, and then solve the type constraints, right? And then there's probabilistic analysis performed by Osprey, published at Oakland 2021. That's actually a very cool paper. So of course, the other problem that we need to think of is, where is the source information about types coming from, right? So one common source is the propagation from the function argument types. So if you know which functions you're calling, you can take the argument types of those function calls as ground truth, and then just propagate them through your binary, right? What if your binary is a statically linked binary? And then you have libraries statically linked into it, and you don't know what libraries there are. This is why sometimes we need a fast library function recognition solutions to recognize what libraries are in use, or what library functions are called. So a little bit more about probabilistic analysis, right? So Osprey is based on probabilistic analysis. Why is it cool? It's cool because when we're doing binary analysis, I'm pretty sure we all realize that there are many cases that after compiling, they become the exact same artifact in binary code, but then in source code, they can be actually different, right? So one example is, let's say you have a struct on the stack, and then your program accesses this struct. What really makes it different from having 3 variables, one in front of another on the stack at the exact same location? Really, there is no difference when you're accessing them, right? But then, only through probabilistic analysis will you be able to choose the more likely, the answer that is more likely to be correct, using not only how these variables are used, but also using other information that's around. Okay. So now the third pillar, control flow structuring. So what does control flow structuring mean? Control flow structuring means, you want to convert the original control flow graph that we built in the binary code, for example, something like this, into a high level structure, such as if then else, right? For this guy, this is if A. If not, let's assume that the left branch is always true, and then the right branch is always false, right? So in this guy, we have if not A, we go to B, otherwise we go to C, right? That's a typical if structure. That's easy. And then if there's a back edge that goes from C to A, we know, hey, this is a loop, right? That's also easy. What's hard? This is hard. Why is it hard? It is hard because the left structure is actually a proper structure, while the right structure is an improper structure. We say it's improper because you cannot easily convert it into a stack of if then else structure that people use in C, because of some of the edges here. They are directly jumping from certain blocks to other blocks that you cannot really do that in C without gotos. So I'll tell you, if I remove those two edges, we'll be able to directly rewrite it into this form, into restructured C form that we all like. The problem is we'll have to leave 2 gotos there, right? One is go to F, the other one is go to G, just because those edges, although we remove them before we perform this high-level control flow structuring, we still need to make sure that those jumps still exist, right? Otherwise, my control flow structuring algorithm is incorrect. Okay. So this is very close to what the original control flow structuring algorithm in Christina's paper did. This is also very close to what the Phoenix paper did, right? So the fundamental problem, as far as I see it, is because our targeting language is C, and C is not expressible enough, right? There are so many different ways for graphs to exist, right? But then, not all graphs can be directly converted into C without gotos. For some reason, we all hate gotos, right? Gotos make code less readable. So here is an example. Certain languages like Ada and Visual Basic.NET, they support multi-level access. So if we have a dialect of C that also supports multi-level access, this is what you will see, right? You see, hey, there's a do loop, and then inside there's a while loop. You can perform break do if you want to quit from the middle directly, and then it directly jumps out of 2 scopes of loops. Can we do that in C? We cannot. Well, you can do that with goto, right? If you don't use a goto, you cannot do it directly. You have to set a flag and then break out of the while loop first, and then outside of the while loop, you need to check the flag, and then you break out of the do. Or you break out of the do while loop, right? So this is one example that tells you that the C that we are targeting is usually not expressible enough. So people came up with innovative structuring solutions, right? One of them is called No More Gotos, published at NDSS 15. The basic ideas are guarding blocks with Boolean expressions. So instead of performing this kind of graph matching based structuring, let's just convert all the graphs, all the blocks with Boolean expressions guarded into Boolean expressions guarded style. And then they also allow the introduction of extra Boolean variables to control which next blocks to act. So at at HCCS 2020, there's a new paper called a comb for decompiled C code that follows a lot of things that normal go-to paper does, but they also proposed a new combing algorithm that is essentially about selectively duplicating nodes to create proper structures that can be properly structured into C structure. So none of them is the final answer. I'll use the normal go-tos as an example to explain why it's not the final answer. So in this one, in our example, the normal go-tos paper will do is it will recover the reaching condition for every single block, and then it will try to collapse and simplify those Boolean conditions for every single block. And then in the end, you're going to have if then else branches for this bit of code. So the problems is that, in fact, I remember this was one of the questions that were asked during the presentation of this talk at the NDSS that year. I happened to be present. So some go-tos actually improve readability in source code, right? This structuring algorithm will remove those go-tos and then replace them with more structured code. Well, maybe that's not a big problem because in a lot of C code snippets, people don't really use go-tos, right? So you don't see them a lot. The second problem is that because normal go-tos rely on the recovery of reaching conditions for every single block, in many graphs, you will actually have really, really long Boolean expressions as the reaching conditions for those blocks. And optimizing those Boolean conditions is very hard, and I can tell you, reading long Boolean conditions is not enjoyable at all, right? This is the human mind. I'm not a set solver. I do not enjoy reading Boolean conditions. What's worse is that the simplification of Boolean operations is an NP-hard problem, right? You may think that simplifying graphs is hard. Yeah, simplifying Boolean conditions is even harder. Okay, so when we actually implement normal go-tos, we realize that in some more complicated graphs, you need to control the simplification, the time that you spend in simplification, because otherwise it's not terminating within a reasonable amount of time, which is terrible. So the research questions I want to ask here for this third pillar of decompilation is, can we make C more expressible? Why do we have to target C, right? Binary Ninja people, Vector 35, they made some very nice first attempts. For example, why don't we directly target HLL, high-level intermediate language that Binary Ninja uses, right? The second question, what really differentiates between good go-tos and bad go-tos? Why are some go-tos good, why are some go-tos bad? I don't know. The third question is, in fact, why don't we study how these improper subgraphs were created in the first place? Because let's say your original code was written in C, right? You didn't insert go-tos. After you use compilers to compile at a certain optimization levels, all of a sudden you have those improper structures. Why were they created in the first place, right? So can we invert the transformations causing these subgraphs? So we'll quickly go through some relevant techniques that are related to decompilation. So the first one is non-function recognition, right? This is very useful when you are using, for example, MSVC that will compile part of their VC runtime libraries into the binary. You want to recognize them, or you have statically linked binaries. You want to recognize which libraries are used, right? So Flirt is a very good one. I believe Binary Ninja has their own technique for identifying libraries. The key point for this is it needs to be fast, right? This is why Flirt is called fast library identification and recognition technique. There are many AI-based function similarity detection papers published in the past several years. Many of them, they claim that they achieve a much better result than what Flirt or other similarity detection papers techniques can achieve. But then, honestly, speed is a major concern, right? Many of them work by comparing functions against functions in the database, and that AI-based solutions, unfortunately, they're not always very fast, right? In a statically linked binary, you have let's say tens of thousands of functions. Good luck using an AI-based solution. So another relevant technique is sharing data and collaborative reverse engineering, right? So collaborative reverse engineering, if you don't know what this is, think about Google Docs. We all know what Google Docs is, right? And think about, when you're using IDA or Gijra or Binary Ninja, you can actually collaborate with your teammates just like you're collaborating with other users using the same Google Docs, So what makes it hard is how can we share the information? How can we synchronize between tools, right? Sharing decompilation artifacts and results between tools is actually more challenging than you may think. So DARPA PM Sergey Bradis gave a very awesome keynote talk at the beginning of this workshop today, and he is a very big fan of Dwarf. Why? Because Dwarf is a open standard for essentially for storing binary artifacts, essentially for storing binary analysis results. It is also generally accepted by many tools, which is great. I just want to make sure that's not a zombie that's trying to enter the room. Awesome. It seems we are safe. Okay. So Dwarf is generally accepted by many tools, right? But then they are accepted with different levels. For example, we tested this, right? IDA, even the latest version of IDA, it doesn't really map or display names for register variables in the decompilation. It does so in the disassembly view. It doesn't do that in the decompilation view. IDA and Gijor have overly strict requirements for Dwarf. Even if we have developed our own library for generating Dwarf information, for generating Dwarf symbol files, if there's anything that IDA doesn't like, the Dwarf file that we generate is still valid. If there's anything that IDA doesn't like, either refuses to load or either crashes. And because it's open, because it's closed source, you have no idea why. So there are also many tools, including Anger, that don't even consume variable names or other types of information from Dwarf files, right? Yeah, you may assume that Dwarf is very open, sure, but many tools don't even care about Dwarf. And finally, Dwarf is just unfriendly to Git or any existing version tools. Like you want to do versioning of a binary format, good luck. It's very hard. Another relevant technique to decompilation is identifying C++ classes, right? This is when we want to decompile C++ binaries. It's very useful. So I'm not going into details here. And finally, I think this is the last. Oh, this is actually not the last one. So another relevant technique is simplifications and optimizations, right? We said there were 3 pillars of decompilation. You achieve those 3 pillars, you will get somewhat okay-looking C code out of it. But then what makes C code, what makes the decompilation output really readable is actually all the simplifications and optimizations that are actually sharing the same root with compiler theories, with compiler optimizations. However, remember that compiler optimizations and decompilation optimizations, they actually have different goals, right? Decompiler optimizations are really for making the code, usually are really for making the code more readable. Right, so sometimes we may need to do certain optimizations differently. Sometimes we might need to invert or reverse some optimizations that compilers did. Okay. Finally, relevant techniques. People are using AI and evolutionary programming into binary decompilation. So, for example, one paper published at BAR 2018 uses evolutionary programming, evolutionary algorithms to decompile binaries and have achieved some interesting results. They actually used byte-level equivalency to test if their evolution outcome is the expected decompilation result. So there have also been some researchers who trained neural networks or neural network-based models to transform machine code into C code, right? As far as I know, nowadays, they only work in a small scale, and it's very hard to evaluate the correctness. How do you know that the output is correct? You actually need to tell if the 2 functions are equivalent, right? If the original source code function and the decompiled function, or your binary function and your decompiled function, you want to tell whether they are equivalent or not. That is not an easy problem. Some performer teams on the DARPA app program, they are making progress, but we are still not there yet. There are also a third genre of work is AI-supported decompilation quality improvement. Right? You can use AI-based techniques to improve the decompilation output, such as predicting variable names, predicting variable types, predicting function names, etc. Some of those papers are Debian CCS 18, Dyer ASE 19, and then Dirty Usenix 2022, which will be published this year. So here's a list of commercial and open source solutions. Right? kind of ranked it, I kind of ordered it based on the quality of decompilation that they generate, but it's extremely subjective. This is how I see them. And of course, this is by roughly April 2022, right? So if you see this video sometime in the future, remember that this order doesn't really mean anything. I really want to say, good job, Hash-Trace decompiler, good job, IDA. There's a reason why IDA is so expensive, because to me, it's still the best overall decompiler that humans have ever had access to. That's open sourced. Oh, sorry, that's open. That's accessible. Okay, so now I need to take some time to talk about what we really need in the next several years. I don't want to wait for another 30 years before this binary decompilation problem is eventually solved. So let's see what we can do to shortcut to get to the final destination faster. First of all, I would like to propose a new decompilation manner called application-guided decompilation. So different decompilation applications may require different decompilation capabilities, right? Let's say you want to recompile a piece of decompiled code versus you want to understand this piece of decompiled code. They may have different requirements for the decompilation techniques that you're using, right? So I just listed a table where Unicode characters doesn't really display, but that's fine. So some techniques are automated, some techniques are automated. For example, automated vulnerability discovery, automated program repair (APR), binary hardening, code reuse versus manual, binary patching, code reuse, program understanding, etc. Right? And you can see that for different capabilities, they actually require different capabilities from decompilers, right? So I do think we are no longer at a stage where you just need to have one decompiler and then some very smart humans to do whatever that's required for your final application. In fact, we should have different decompilers or customizable decompilers for different applications in the end. And we're also looking for more AI-powered techniques, right? I do think right now end-to-end AI-based decompilation is a little bit too early. But what we can do is there are many problems in decompilation that can be solved using AI. Because fundamentally, a lot of them do not have one correct answer, and many of them do require the use of probabilistic algorithms, right? Such as variable type inference, name inference, control flow structuring, even many simplifications should be able to be powered by AI. We should also explore more decompilation capabilities, right? For example, flexibility. I've seen people complaining about the rigidness of decompilers, mostly Ghidra and IDA, on Twitter. Right? There's one person who claimed that he would kill if IDA would allow him to invert the if condition in the decompilation output. Honestly, I think that's not a lot to ask, right? But nowadays our decompilers don't really allow you to do that. The other thing, I think this is also mentioned during the morning keynote, was bidirectional transformation. If we're making changes on the decompilation code, how can we make sure the same transformation, how can we make sure the same change is applied on the original binary code as well? Right now, the only solution is you hope for the best, you pray to God that the decompiled function is compilable, is correct, you take it, you compile, if everything works, you put in your changes, you manually patch in the bytes to the binary, and that's it. It's a very annoying and tedious process. What if I just want to change a constant? What if I want to change a string? What if I want to negate a branch? What if I want to replace, what if I want to swap two if then else's branches, right? So I think directly applying changes in decompilation on binary code is very important. And finally, there's customizable decompilation, right? We all know that compilers have many flags, right? And most of us, we only specify -00, 01, 02, 03, or OS. We don't even use other flags. But they are there for us to use. Where are the decompilation flags? Where are they? Why are decompilers so unconfigurable nowadays? Okay, the topic of my talk today is scientific binary decompilation, right? So we actually need to talk more about the science in decompilation. So what's the difference between a scientific solution versus an arbitrary solution that someone else on the street came up with is, if anything is science, we should be able to measure it, right? If we want to measure science, we need a matrix. But then I realized that many concepts in the decompilation is actually not very well defined. For example, what does readability mean? How can we quantifiably measure readability of source code, but also of what is the readability of decompilation output, right? And also, what does readability mean for reverse engineers? What does it mean for grad students? What does it mean for different people, for different groups of people that will consume the decompilation output, right? We can repeat this process for correctness, completeness, for many other concepts that are critical for evaluating the quality of decompilation output. Without being able to measure the quality, it's very, very hard to tell if technique A is better than technique B, or technique B is better than technique C, right? So I also want to talk a little bit more about scientific evaluation. So when we're evaluating, decompilers, right, we need to evaluate a lot of things. And when we are evaluating decompilation techniques, we also need to evaluate a lot of things. One thing that's missing for many decompilation papers is the evaluation of correctness. How do you know your decompilation result is correct? Usually people just assume that their decompilation technique works correctly by construct. However, sometimes it's not the case, right? Then we also need to evaluate the conciseness, the readability, the recompilability, completeness, etc. There are many, many things, right? Properly evaluating decompilation techniques is actually pretty hard. So to continue with that, honestly, I feel modern decompilation papers are usually not as rigorously evaluated as many other binary analysis papers, right? So, for example, many decompilation papers, they only use Ruoyu binaries to evaluate. Ruoyu is a good set of binaries. One problem, but there are not a lot. And one problem is that they have a high number of duplicated functions in many binaries because they just share the same code base. There are also papers are evaluated using 3 malware samples. They are not obfuscated. They're also unpacked. And I have no idea why those malware samples are special. What really make them special? What really make them reflect the real-world use cases for decompilers, right? And sometimes you see evaluations running on binaries that are compiled using the same version of a compiler. Does it generalize to other compilers? I don't know. And sometimes, it's just fundamentally it's unclear how well the techniques that papers propose work on real targets, right, on real-world binaries. I also want to say that failures are actually useful, right? When we're writing papers, we have this typical mindset of only 100% successes can be published, only 100% successes should be published, and the future work section is fundamentally useless. But I would like to call for the fact that we are actually working on scientific papers. We are not working on commercial ads, right? We don't need 13 pages of text to just say that how good our techniques are. The papers are a way for us to communicate with other researchers. We do need some frank analysis and discussion so that others can truly understand the strengths and pitfalls or the strengths and drawbacks of any new technique that a paper proposes. You should not always leave, it to other performers, to other researchers to figure out what the pitfalls, what the drawbacks there are for your technique. Okay, so after we talk about metrics, right? Another important problem for evaluation is the data set. So Brandon Dolan Gavitt stressed the importance of cross data set generalization during his keynote speech on BAR 2018. I think nowadays for binary fuzzing this is becoming much better, but for decompilation, there's still a lot that we need to do. The idea is that you want to understand how well a technique developed and evaluated on one data set, how well does it work on a totally different data set, right? This actually means, we need more than one large and real data set in our field. But one thing that we're still waiting for in decompilation is the very first data set for decompilation that people all agree to use. So we need to measure the quality of the data set to see if it reflects the characteristics of real binaries, if it reflects the characteristics of modern compilers, and then if it captures the problems that technique A aims to solve, right? There are some examples of low quality data sets. I'm not going into details because of time. Let's move on from here. So one problem that I mentioned just now is the cross-tool collaboration, right? Which means information sharing between tools is not an easy job. So our first attempt is a tool called Binsync. Binsync is an open source solution. You can access it at this URL. It provides a unified textual representation format of reverse engineering artifacts plus a Git-based version management. So it allows a fine-grained control for users, for different users using different tools that are working on the same binary for them to share their annotations, such as variable names, variable types, structs, and comments, and etc. On the same binary. So right now it supports either Binary Ninja and anger management. It has very preliminary support for Ghidra just because how hard it is to write Python 3 code for the modern Ghidra. Evaluation against existing solutions. So I'm one of the authors for Anger, so I realized that in many papers, researchers evaluate binary analysis techniques on or against Anger. But one thing that many people didn't really think of is Anger bug-free, right? How do bugs in Anger impact the evaluation result? And how much of the improvement is actually due to a more correct implementation that the paper authors have instead of the actual improvement caused by the technique itself, right? I can tell you that Anger is not bug-free. If you take a look at the PRs that are recently merged into Anger, search for bug, you will see many of them. What does that mean? That means we are fixing bugs all the time, right? So after those bugs are fixed, many evaluation results that are published in the past, they no longer apply. I'm sorry to tell you this, but that is true. So our first attempt in this problem to solve this problem for decompilation is a system called MDAC. So MDAC is actually a pretty simple tool that will allow you to compare decompilers' output from different decompilers. Hey, Anger might be buggy, but how about other decompilers? IDA might be buggy, how about Ghidra, right? Or Ghidra might be buggy, how about Binary Ninja? Right? So MDAC, I believe MDAC supports more than 8 different decompilers nowadays. You can actually use it to easily compare decompilation output between different tools. And if there's a bug, it should be easy for you to identify it. It no longer goes to the next slide. This is almost the end of the talk, but you should still allow me to go to the next slide. Oh, thank you. Appreciate it. Awesome. So this is an interesting quote that I got from Jordan, one of the major person in Vector 35, one of the major person behind Binary Ninja, is that when something fails, right? The actual reason was because the Binary Ninja developers haven't seen such a case yet. If they have seen such a case, they would have fixed it. Makes sense. But then, from a research perspective, what we really want to ask is, how many cases are actually sufficient for us to capture, for us to achieve perfect decompilation, right? Where are these cases coming from? And also, which decompiler will work best on which binary, and which decompiler will work best on this binary? Okay, well, these are all the things that MDAC will help answer. Okay, engineering effort. We didn't see a lot of decompilation papers published. One of the reasons being, working on decompilers is very, very hard. You don't necessarily have access to a decompiler in the first place, and you don't necessarily have access to a flexible and usable decompilers that have existing techniques implemented. right? If you want to compare your decompiler, if you want to compare your new technique against an existing technique, you have to implement the techniques in the first place. That itself, to many people, to many grad students especially, is a waste of time. So, it's worse that most decompiler paper authors, they didn't release their tools, they didn't release their artifacts, right? Or they only released their solutions after several years. I have no idea why, but releasing is always better than not releasing it. So we really need an open source, powerful and flexible decompiler where, to make sure that techniques can be developed on the same platform and they are actually comparable against each other on the same platform, right? So our first attempt is Angular Decompiler. Angular Decompiler is fully open sourced. It implements quite a few techniques. It also has a very accessible GUI that allows you to enable and disable configurations as you want. And our goal is to build an open binary decompiler community. No matter what decompilers you use, we are all part of this community. We're all here to foster the research in this field. And last but not least, it's a matter of what we really need is research interest. And of course, for researchers to work, we need financial support, right? So one thing that I like to mention is, we really need more powerful attitude towards real-world learning research, including binary decompilation research, okay? I've seen this in the past, right? Some of them from my colleagues, some of them from paper reviews, some of them just from, chatting with other professors. For example, decompilation has no security applications. We all know that's false because of the number of decompilation papers that are published at security conferences. Second, decompilation has ethical concerns. People are asking, why do you try to decompile binary code? Because they were designed to not be understandable, not be analyzable by you in the first place. And we all know that's BS, right? I'm not going to call that out here. And third, with the information that the decompilation needs, one can already build good vulnerability discovery techniques that work on binary code. You don't need to do this one more time, right? You don't need to decompile the binary code into source code and then do source code-based analysis. So it's this is an argument that seems reasonable, but in fact it's not, right? Because only with decompilation can we enable the use of source-based tools on existing software that source-based tools do not work on, right? That will be a very big save of resources. That will be a very big save of energy that you cannot really achieve otherwise, right? So I would say, anything that makes decompilation easier, anything that makes decompilation feasible, anything that makes source code-based tools more applicable or more targets, they are actually of scientific value. And of course, we would like to thank research funding from the government and the industry, right? So as far as I know, the very first decompilation-related DARPA programs is CHESS, started back in 2018 or 2019, and also Sergey's program called DARPA AMP, where one of the technical areas literally called retargetable decompilation. So I believe decompilation will enable a wide range of new capabilities. And with your support, with everyone's effort, we are on our way of making decompilation a real science. So with that, let me know if you have any questions. And here are the links for the tools that we mentioned during this talk. Thank you very much.